Hello, welcome to the 15th talk of the Chromatic Motions seminar. Today we have a special guest. We have Jonathan from University of Nevada, who will talk about Picard spaces and orientations. So, Jonathan, please take it.
Sure. Thanks, Amartya, for asking me to do this. I'm sorry, I was supposed to do it last week, and things got kind of messed up. So I had to. Well, I didn't show up, so I apologize. Yeah. So this is yeah. I mean, I figured I'd just kind of give a rundown on how some of this stuff works. I don't really know what the expertise level of the seminar is, so please feel free to interrupt to ask questions or whatever. I think this will be a lot of review for Shahar in particular, but but okay. So what's the basic setup here? I want to have, in general, some symmetric monoidal infinity category. And I am going to define this space, which I'll write as pic C, to be the maximal sub infinity groupoid of this category C on the tensor invertible objects. So I'm going to take now I've got this tensor product in C, and I can ask, given an object, is there some other object such that when you tensor them together, you get the monoidal unit back. So that's some infinity groupoid. In particular, I'm taking these objects and I'm only taking equivalences between them. And it's closed under the tensor product. If you think about you tensor two invertible things together, then you still have an inverse. There is a faithful symmetric monoidal inclusion from this infinity groupoid into C itself. So anyway, yeah, so this is an infinite loop space. This is one of my favorite things about working in the infinity categorical framework, is that this is a space, it's an infinite loop space, but it, includes into a category. So this puts all of this stuff kind of on the same footing in a really useful way. And then just some notation. Pixie has a base point, which is this object 1 itself. And I'll write BGL1 of BGL1 of 1 for the connected component of that base point. It has a canonical base point as an E infinity space, as a unit. And GL1 will be loops, sort of not surprisingly, on that infinite loop space. So a comment about that, so I've essentially defined things in this very leading way, but of course it's true. And most of this stuff is in one of two papers, either the sort of the 5-author paper, ABGHR, Ando-Blumberg-Gepner-Hopkins-Rezk, on this sort of stuff in the infinity categorical setting. And there's also another paper of Ando-Blumberg and Gepner on parameterized homotopy theory, which sort of talks about the Picard space in particular. But of course, a lot of this stuff goes back much further. There's old papers of Mike Hopkins and a book by Peter May on May and others on this sorts of stuff. So it's old stuff. But okay, so what's the proposition? If you take this Picard space and you take loops on it, that of course is equivalent to loops on this space BGL1 of 1, which is this GL1 of 1, which is going to be automorphisms in C of this unit object. So this is a thing that deserves to be called GL1. So a fun example that is basically what we're going to be focusing on for the entire talk is R is going to be an E-infinity ring spectrum. And our category C is going to be the category of left modules over R, left module spectra. In this case, I'll write pick R instead of pick L mod R. And then similarly for GL1 of R and BGL1 of R. The other nice thing about this situation is that you can give a really concrete description of this space GL1R. So there's a pullback square that GL1 of R participates in, which is basically, you notice that loops infinity R by truncating maps down to pi 0 of R. And then you can take, because R is a commutative ring spectrum, pi 0 has a ring structure. And so you can take the units and include them in there and then take the pullback there. So all this is really saying is that GL1 of R really is basically loops infinity R, but you've just taken the sort of components that live over invertible things in pi 0. Yeah, I feel like maybe there was something else I wanted to say about that, but let me also mention that these spaces are all infinite loop spaces. So they have corresponding spectra. Which, yeah, and so of course this, I didn't say this explicitly, but this only happens when R is E infinity. If R is just an EN ring, you still have these spaces, but they're only, well, EN minus 1 monoidal spaces. So in which case you don't have corresponding spectra. So usually I'll just write these using lowercase letters, GL1R, BGL1R, etc. Another thing to note about this is GL1R is equivalent to GL1 of the connective cover of the ring spectrum R, basically because it's built out of loops infinity, and loops infinity ignores non-connective stuff. And so by delooping, the same thing holds for BGL1R. But this is not true in general for the Picard space. So, BGL1R is sort of one component of the Picard space. So it's pi 0 is trivial, but the Picard space has potentially more than one object. And so its pi 0 will not, will typically be sort of more complicated than BGL1R, and it will take into account non-connectivity of R. So here's an example. Let's let R be complex K theory. So periodic, non-connective to periodic. And it's in general true that sigma I of R is invertible. Why is this true? Since sigma I of R tensored over R with sigma negative I of R, that's equivalent to SI tensor R tensored over R with S negative I tensored with R, which is of course equivalent to S tensor R. So suspensions of your base ring are always going to give you elements of the Picard space or objects of the Picard space. But of course, Ku is periodic. So we only get two objects this way. So we have Ku itself, and then the one-time suspension of Ku in pic Ku. So pic Ku has at least two objects. I mean, it's pi 0 then has at least two elements as a group. And it's a theorem. I think this is probably a pretty old theorem. If you're in the algebraic topology Discord, then I actually asked this like 2 hours ago because I didn't really know who to attribute this to. But it seems like it only appears concretely in this paper of Matthew and Stoyanowska. And the theorem is that indeed these are all of the invertible Ku modules. So pi 0 of pic Ku is a Z mod 2 generated by Ku and a suspension of Ku. So there are no other invertible Ku modules. On the other hand, consider connective K theory. In this case, you don't have any periodicity. So your suspensions don't ever sort of repeat themselves. And so pi 0 of pic of connective Ku is in fact the integers generated by well, I guess I should not have said generated previously, right? I mean, it's generated by Ku. And then down here, the generator is again this little Ku. So quite a few computations have been done to understand these things. Maybe one quick thing to mention is that because of the way it's constructed, pi I of this GL1 R is pi 0 of R cross, so the units in pi 0 of R when I is equal to 0. And then for higher homotopy groups, it's just pi I of R, because those are the homotopy groups of loops infinity R. So that tells me that essentially knowing the homotopy groups of, well, not essentially, I mean literally knowing the homotopy groups of GL1R is the same as knowing the homotopy groups of R itself. And so computing, and then loops on pick R is GL1R. So knowing the higher homotopy groups of pick R are the same as knowing the homotopy groups of R itself. So this pick R is really sort of where a lot of the interesting stuff is happening, or pi 0, I should say. And so there are a lot of computations of this stuff. It probably won't surprise you that pi 0 of pick S is, again, the integers, just using this suspension situation. Pi 0 of pick of KO is Z mod 8. And again, this is a somewhat recent result of Matthew and Stoyanowska. Let's see, what are some other interesting ones? Pi 0 of pick of non-connective TMF is Z mod 576. There's this related sort of compactified TMF, which is somehow in between connective TMF and non-connective TMF. And this actually kind of has an interesting Picard group. This capital T lowercase mf is not connective, but it has a Z, and then it also has a Z mod 24 sitting there. And then in general, I guess I should say that usually this might be true very generally. I'm not sure, I guess, but it's typically not that interesting for Eilenberg-MacLane spectra. So this is also true, for instance, of like HQ. It's also just the integers, again, given by suspension. One collection of Picard groups which are not well known in general and are the area of sort of ongoing study are, so pi 0 of pick of, if you take the localization of the sphere at En, Morava E theory, this is not in general fully known. And similarly for the Kn local sphere. So people seem to be pretty interested in knowing what those are. And in many cases, they're not known. All right, is that okay? Any questions or anything? All right, so definition, an R-line bundle on an infinity groupoid X is just a map of infinity groupoids from X to pick R. The colimit of the composite X to pick R to L mod R is called the Thom spectrum of F. And it's just denoted MF. So there's some nice things about this spectrum. Oh, and maybe I should say, notice here that this will sort of be relevant later, is that MF is, of course, an R module. So it's in the sort of model category theoretic framework, it's a theorem of Gauss-Lewis's, but more recently, Antolin Camarena and Tobias Bartel proved that taking this colimit is symmetric monoidal. So the functor that goes from spaces over Picard to modules over R, which takes x over Picard to this MF thing, is symmetric monoidal. With respect, I should say, with respect to the day convolution monoidal structure on spaces over Picard. Remember, by unstraightening, or rather straightening, I guess, spaces over Picard are equivalent to presheaves from Picard into spaces. And so because Picard is an infinite loop space, this inherits a day convolution monoidal structure. Okay. So that's one useful thing. We can get, if we start with a map of, say, En spaces from X to Picard, then the associated Thom spectrum is going to be an En ring spectrum, which is often pretty useful. Or, well, in particular, the associated Thom spectrum is going to be an En R algebra, not just a En ring spectrum. So a lot of this, I mean, the whole Thom spectrum picture is really pretty classical, and some of you, or all of you, are probably familiar with the Thom spaces showing up in sort of classical algebraic topology, in sort of like in Milner and Stashov's book, for instance. So what's the relationship here between these sort of classical things and this infinity categorical stuff we're doing here? I think it's probably useful to look at a sort of specific example. So remember, there's this thing called the J homomorphism, which describes an action of the infinite orthogonal group on the sphere spectrum. Roughly think about it as, orthogonal groups at any finite level act by automorphisms on Sn itself, and then, very, very, very roughly, you sort of let it go to infinity, and you get an action of the infinite dimensional orthogonal group on the sphere spectrum itself. And this thing is pretty useful. It tells you a lot about chromatic height 1 stuff happening in the stable homotopy groups of spheres. It's used by atoms to do a lot of pretty amazing stuff. And so here's a theorem. Again, probably originally this goes back to May, but of course is also written in this framework in ABGHR. And what it says is that the colimit of this map, BO to BGO1S to spectra, is indeed the classical Thom spectrum MO, whose homotopy groups give us the real cobordism ring. And then just that this is basically generally true for any of your classical cobordism spectra. So you have the sort of diagonal matrix map from BU to BO, followed by the J homomorphism. This gives you the complex cobordism spectrum. And then you can do this for whatever you want: MSO, MSU, M spin, M string, anything that maps to BO, you can do this for. And the way that this is proven essentially is that, for instance, in the infinity categorical setting, ABGHR, what they essentially prove is that the Thom spectrum functor, this sort of symmetric monoidal co-limit preserving functor that goes from spaces over pic R into R modules, is up to homotopy, is unique. And so then they show that these sort of other constructions of MO and MU and so forth also give a Thom spectrum functor, and so the resulting things have to be the same as the classical things. So some important things to recognize. If you give me a map from X to pic R, which is null homotopic, then this spectrum MF, this R algebra spectrum, is equivalent to R join the space X, by which I mean take R and tensor it with the suspension spectrum of the space X. So this is sort of like the R algebra generated by the space X. And that's, I mean, depending on how you define things, that could be a definition. If you want to define the tensoring in an infinity category over spaces, you literally take the map from, or rather take the functor the constant functor from your space to whatever object, in this case R, and then you take the colimit, and that's how you define things to be tensored over spaces. But I think it can be sort of a fun exercise to try to think about why this should be true. You know, it's sort of this picture of X inside of R mod, where every map is the identity, and then you're taking the colimit of this. What does that sort of thing look like? On the other hand, if you give me phi from R to A and R algebra, or a map of commutative, or I guess in this case, I just want to say EN R algebra in general. Then the colimit of the composite. So I'm going to start from X. F is going to go to pic R. You can tensor invertible R modules over R with you can base change them up to A. And this lands in pick A. And then I can take the colimit, which lands in L mod A. And the thing that I'm going to get is just whatever the Thom spectrum of MF was, tensored over R up to A. So taking Thom spectra commutes with base change. And again, maybe this isn't so surprising. Tensor product is a left adjoint, so it should preserve colimits. And that's exactly what's going on here. You're just taking, you've got your diagram, your X-shaped diagram. It's got an R at every vertex, and then you're tensoring every vertex with A over R, which just gives you an A-shaped diagram, and then you're taking the colimit of that. So those are two useful facts that'll come up again later. One sort of interesting thing about the sort of doing this higher algebraically, I mean, this is in general true, but these sort of statements classically were really only known in the homotopy category. So first of all, M of the trivial map. So colim of X, contract to the point, and then map that to the base point of pick R is, well, we've already talked about, this is R join X, and this is a co-commutative R coalgebra. So a coalgebra object in left R modules. And it's a bialgebra if X has some En structure. And then one result of this is that for any F from X to pick R, MF is an R adjoin X co-module. And so you can prove this sort of categorically. But this then recovers a sort of very classical thing, which is called the Thom diagonal. Well, over R with R adjoin X, which is just MF tensored with X. This is essentially, you're essentially getting this by taking the diagonal map on your space X, then X via F maps down to pick R. And then on the right-hand side, you take the Cartesian product of the map F on the left-hand coordinate crossed with the trivial map on the right-hand coordinate. You can check this pretty clearly commutes. Again, I mean, this is old, I think, stated in this way, you know, it goes back to Mahowald, for instance. But stating it just in this way only gives it to you in the homotopy category. You have to do, it's kind of unpleasant to make it all work with all this higher structures, that you actually have an honest E infinity co-module structure. Okay, so here's a definition. Amartya, this is an hour, right?
Yeah, that's right.
Okay. I mean, I guess if it was shorter, then I would, you know, I don't know what I would do. Okay. So a Thom spectrum, MF, is called A-oriented. here I should say for an R algebra. If the composite from X to pick R to pick A is null homotopic. So that's there are several definitions of being A oriented. This is, I just think, sort of the simplest to state. A lot of this stuff, I mean, a lot of this stuff is also, I think, covered in more detail in this paper I have on the archive about bialgebras and descent data and so forth. So here's another theorem. Again, really going back to Gauss-Lewis, but also in ABGHR, Ansel and Camarena-Bartle, which is that MF is A-oriented. If and only if there is an R module map from MF to A itself. And then you can also ask about sometimes what are called EN orientation. So if MF is an EN R algebra, then you can ask for that map to be a map of R algebras, which is so it's sort of a stronger notion of being oriented when you've got a ring spectrum. Another nice theorem of Ansel and Camarena-Bartle is that MF is always, in particular, MF oriented. Oh, and I guess I should say whenever MF has an EN structure. Induced by an EN map from X to pick R. Okay, so because of this symmetric monoidality of the Thom spectrum functor, if you have an EN map, then MF becomes an R algebra, and then you can ask if it's oriented with respect to itself, and it always is. So one thing then that happens is that you get now the Thom isomorphism. So if MF is A oriented, there is a Thom isomorphism. From, so if you take MF tensored over R with A, and then you apply this Thom diagonal on the left-hand side to get MF tensored. Well, let me flip it around, which everything's commutative, so I'll write it this way: X tensored with MF tensored with A. Then you apply your orientation. So X tensored with my orientation U, tensored with A, takes me to X tensor A, tensor A. And then I can apply the multiplication of A to land at X tensor A. And being Thom isomorphism means that this is an equivalence. So, or rather, being oriented means that this is an equivalence. So it might be helpful to think for a moment about why we're using the term oriented here. And the short answer is that, classically, you talked about a bundle being oriented when you could essentially trivialize it for some in some homology theory. And it's the same thing going on here, but it's sort of a much more general statement. But okay, so what's the classical situation? The classical example is that you start with some map, so some bundle F, some real vector bundle on X. This has an associated Tom space. X superscript F. And probably I should have said this earlier, but a useful fact here is that if F from X to BO is a finite dimensional, and I guess I should have said this bundle up here needs to be finite dimensional for this really to make sense, is a finite dimensional vector bundle, then this spectrum MF coming from including mapping BO via the J homomorphism to BGL1S and then taking the co-limit is exactly the suspension spectrum of this Tom space. So this still retains the sort of classical constructions of Tom spaces from vector bundles. Now let's ask that our vector bundle be oriented. So we say F is oriented if there exists a lift. You've got your F here. And then you can take the simply connect cover of BO, BSO, and you can ask for there to be some lift. So you can you lift the structure group of your vector bundle to SO? So let's suppose we're starting with that. Or rather, not X here, but F. So it's some finite dimensional oriented real vector bundle. And then we want to consider this composite. X to BO, that's factoring through BSO to BGL1S. And from BGL1S, you can further go to BGL1 of HZ. Now, remember, GL1 of HZ, well, I suppose I didn't say this, but when you take an Eilenberg-MacLane spectrum, its unit space is just the units of pi 0, which is the units of the ring of which you took the Eilenberg-MacLane spectrum of. So maybe I should write that down. And note, that GL1 of HZ is equivalent to just Z cross with the discrete topology, which of course is Z mod 2. So in this case, BGL1 of HZ is isomorphic or equivalent to BZ mod 2, aka RP infinity. And so now let's think about this composite we just wrote down. So we've got this composite, but we've replaced BGL1HZ here with BZ mod 2. And then think about the sort of internal composite here from BSO to BZ mod 2. You may know that homotopic classes of maps from BSO to BZ mod 2 are the same as H1 of BSO with coefficients in Z mod 2. And by the Hurevich theorem, that's 0. So there are no non-null maps from BSO to BGL1HZ. So if X is oriented, or if F is oriented, this implies that HZ tensored with MF, because this is, of course, now I'm going to take the co-limit into L mod HZ, and that's going to give me some Tom spectrum. But from earlier, we know that this is just whatever Tom spectrum I started with, equivalent, tensored with HZ. That's going to tell me that this is equivalent to that Tom spectrum. I can just replace, it's going to be the trivial Tom spectrum now. So I can replace this with HZ tensored with X itself. But in this situation, MF was my Tom space. And so the resulting fact here is that, and so this is, is that H star of my Tom space with coefficients in the integers is isomorphic to H star of the base space of my bundle with coefficients in the integers, which is sort of the classical Tom isomorphism that relates the homology of the Tom space to the homology of the base space of your vector bundle. And so, of course, what is this? If you think about this, what is this saying? It's saying, look, I've started with an oriented vector bundle, and then that implies that this composite here is null homotopic. And so the Tom spectrum of this thing is HZ oriented in this language that we've already introduced, which goes back to this classical case of the vector bundle itself being an oriented vector bundle. Same thing happens for complex vector bundles. Every complex vector bundle is oriented, so you get the same thing in that situation. And more generally, you get things like MSO tensored with HZ is equivalent to BSO tensored with HZ. You get Tom isomorphisms for all these Tom spectra. These are sort of the universal examples of having these vector bundles, or MU tensor HZ is just BU tensor HZ. So MU and BU have the same homology, for instance. The other thing to note, though, is that BGL1 of HZ mod 2, well, this is going to be the units of Z mod 2. So that's just going to be a point. It's going to be the trivial group. And so what this means now is that if you have some vector bundle F, you go via the J homomorphism to S, and then you go further to BGL1 HZ mod 2, which is just the point. Ah, sorry, I made a mistake up there. That shouldn't say BGL1 HZ mod 2, it should say GL1 HZ mod 2. So that's always going to be null homotopic, which then tells me that in general, for any vector bundle, the homology with coefficients in Z mod 2 will be isomorphic to the homology of the base space with coefficients in Z mod 2. So this is sort of the unoriented Thom isomorphism. And in general, of course, one thing that this tells you is that, for instance, every Thom spectrum over the sphere is HZ mod 2 oriented. Let's see, how are we on time? I guess well, maybe we started a little bit late. Are there any questions about any of that?
This is a really dumb question. So there's some shifting in the grading in the classical case. How does that sort of appear here?
I brushed that under the rug. What I'm doing here is that really, if I've got some vector bundle, really where I'm landing is here, and that Z component is telling me the dimension of my vector bundle, and then this maps to BGL1S cross Z, which is pick of S. And so I can ask I can then consider what happens there. The only real difference that this makes is that if I had some vector bundle here, then MF, instead of being the suspension spectrum of my Thom space, it's going to be the n-fold suspension of the suspension spectrum of my Thom space. And then if you redo everything we just did and you write it all down, then the Thom isomorphism will have a degree shift living in it. What I've secretly done here, which doesn't actually affect anything, is that I've taken my n-dimensional vector bundle and I've taken it and then subtracted from it the n times the trivial bundle, which then pushes it back down into BO cross 0. And then that gets rid of the shift. And I think maybe the sort of reason this was done, I guess, classically was that, people really were just kind of thinking about BGL1 of the sphere spectrum. They weren't so much thinking about the Picard spectrum of the sphere spectrum, because the J homomorphism gave you this really sort of nice approach to GL1 of the sphere spectrum, and then the natural sort of thing that you get from that is a map from BO to BGL1 of the sphere spectrum. And so you kind of you need to figure out a way to make sure you land in an actual sphere bundle instead of a bundle of shifted spheres. Yeah, that's a good question. And actually that was something I was very confused about for a while. So yeah, it's all kind of brushed up.
Yeah, thanks. Yeah, that helps. Thanks.
Anything else? So maybe there's one other aspect about this stuff that I'll mention, which is that there's a sort of Galois structure for these things. So now what I want to do is I want to start with the data x2, and maybe I'll stick to BGL1R here just to avoid having to lie in any way. So now let's say that this is a map of infinite loop spaces. So what did we see before? We saw that we had this Tom diagonal. And now this is a map of, sorry, not MF. This is a map of R algebras in particular. And then we also have the Tom isomorphism, the MF Tom isomorphism for MF. So MF tensored with itself over R to MF tensored with MF tensored with X, and then you apply the multiplication of MF to land back down in MF tensor X. And this is an equivalence. So you have these two structures. And then you can do, assuming that you believe this makes sense, you can take spec of this whole picture to get affine spectral schemes, if you like. Or you can just think about the arrows as going the other direction. But let's take spec and notice one thing, that Rx is, in this case, a co-commutative R bialgebra. In fact, it's a R Hopf algebra because it has by reversing the direction of the loops, you get an antipode. So maybe we'll write. So spec of a co-commutative bialgebra gives you affine group scheme. So I'll just write this as G for now. And so what do we get? We get spec of MF, and I'll just write cross over R, by which I mean crossed over spec R. So because this was a co-module, this now becomes has a sort of a G action on spec of MF. And then you also get that spec of MF crossed over R with G. The first thing you can do is you can apply the diagonal map of spec of MF because it's just the opposite of the tensor. And then you can use the G action on spec of MF. And again, that's an equivalence. And what this is telling you is that spec of MF is a G-torsor. Over spec R, aka a principal G bundle in the sense of, well, say on spec R. In the sense of derived algebraic geometry. So when you take Tom spectra, you're sort of going from one kind of bundle to a different kind of bundle. And maybe the last thing I'll say is that we can ask the following question about a G-torsor, which is that if I take the thing living over spec R and I take the quotient, and really here we mean this sort of stacky quotient, the homotopy quotient of this action, do I get back the base space? Now you get this sort of in general. I mean, this is part of the definition really of being a G-torsor in classical algebraic geometry. And you basically get this for free from this statement up here. But in this situation, this isn't always the case. So this is a question. And for instance, this isn't a complete answer, but the answer is yes, if, for instance, pi 0 of mf is isomorphic to pi 0 of r. And this quotient gives a spectral sequence. One way to think about it is that how would you write down that quotient? You'd write down that quotient as a simplicial object. You'd sort of look at the action groupoid of G on spec MF, which would be this big simplicial thing, and then you take the co-limit, and that would be the quotient. That corresponds to a co-simplicial object in our algebras, and then you take the limit, and a co-simplicial object has an associated Bausfield-Kahn spectral sequence. So this is one way to get this spectral sequence that I'm talking about, which maybe I'll say this. In the case of spec of mu over spec of s is precisely the mu-based Adams-Novikov spectral sequence. So this is a sort of, so in other words, the Adams-Novikov spectral sequence is really a descent spectral sequence. Yeah, maybe, I was thinking there was one other thing I might like to say. Oh, just to point out, oftentimes people talk about a spectrum E, a ring spectrum E being complex oriented, i.e. having a ring map from mu to E. That's not the same as being oriented in this sense. This is a different thing. Okay, that's it. Thank you for listening.
So yeah, first let's thank our speaker. And I think we're open to questions, more questions.
Hi, I had a question about the day convolution part.
Mm-hmm.
So I get that. So you have this monoidal structure on three sheaves on the Picard space,
Mm-hmm.
right? But if you have like two pre-sheaves whose like total space after unstraightening is S, and if you sort of take the monoidal product, is there an easy way to see that the total space of the product is also S?
Oh, let me see. So maybe if I'm understanding correctly, is the question something like so maybe part of the question is what do I want to say? Well, maybe this will give you a partial answer. One way to think about what the day convolution monoidal structure is on space, so unstraighten to get things living over pic of S, and then I can tell you really clearly. And you'll tell me if this ends up answering your question. Oh my gosh. So what is the day convolution tensor product of? Actually, let's not necessarily. So something like this. Well, basically what this corresponds to is you take X cross Y, so let's call this F and G. You have some map F cross G down to pic R cross pic R. And then pic R as an infinite loop space has a multiplication on it, landing in pic R. And so I suppose if you take X itself to be, yeah, I didn't, does that answer? Or
Yeah, I think that helps. Yeah, that's
okay.
basically what I was asking.
Yeah, I mean, I think that's a much easier way to think about what the day convolution monoidal structure is in this case, rather than, you know, sort of looking at this horrible con extension formula.
Yeah, thanks. Makes sense.
Maybe one other thing to point out is that this has another monoidal structure which corresponds to the pointwise monoidal structure on pre-sheaves, in which case you just take if you've got two things like this, you can of course just take their pullback. And that's that also gives this category of spaces over pic R a monoidal structure, but this is not kind of what you want in terms of what sort of symmetric monoidal structure the Thom spectrum functor will preserve.
Right.
Yeah, and maybe does this also answer the question of like what? I mean, I guess it does. I mean, this is supposed to also answer the question of why an EN map from X to pic R should be thought of as an EN algebra in pre-sheaves on pic R. Because when these are both, when they're both X and these are both EN maps, then you can equivalently go from X cross X to X itself and then down to pic R. And because that's a map of, because the map from X to pic R is an EN algebra, this diagram commutes. And so then you get that X comma F or whatever is an EN algebra in the category of spaces over pick R.
All right, we have more questions. Yeah. If not, let's thank our speaker again. And then I'll post updates about the next talk. So, okay, maybe I can stop recording now then. Brief.
Me, yeah.